Ladies and gentlemen, we are now about to begin the plenary forum session featuring invited speaker. Let me introduce our speaker, Dr. Amirreza Shaiganpour. He is a researcher at Istituto Italiano di Tecnologia, Italy, since 2017. He received his PhD degree in Materials Engineering Science from the Department of Bioengineering and Nanotechnology at the University of Genoa in 2017, and his master degree is in Advanced Manufacturing Technology at University Technology Malaysia in 2011. He is also appointed as a materials scientist for polymer composite material development at the Nanoramic Laboratories in Boston, USA. His research efforts are primarily focused on functional coating, specializes in energy storage technology and material solution based on nanocarbons, advanced materials for packaging, and thermal interface materials. Now, without further ado, we proudly bring to you our honorable, respected speaker, Dr. Shaiganpour, to deliver for his plenary speech. Please welcome Dr. Shaiganpour. Again, 45-minute time is all yours. Please.
Good morning and good afternoon, and welcome to my presentation. First of all, let me thank you all for joining here today. So here we go. Let's check. Yeah. Okay, I can see my screen, and let me check the monitor. Yeah. So thank you all for joining here today. Let me start by saying a few words about my own background that mentioned before coming to Italy and start my PhD, I got my master degree in advanced manufacturing technology in University Technology Malaysia, UTM, in 2011 that I really appreciated. So as you can see in the screen, the topic is thermally conductive non-composite using sustainable materials and process. First of all, let me explain a little bit about the place that I'm working and living here. So Genoa is the port city and the capital of the Northwest Italy's Liguria region. And this is the most important, the harbor in Italy and one of the main harbors in the Mediterranean Sea, and located around 120 kilogram to Milano or around 200 kilogram from the south of the France, as you can see in the map. So it's one of the largest heuristic centers in Europe with the great art and a lot of museum. So some of the tastiest food in Italy is same like the pesto. So, okay, I will not keep continue about food to have your focus. Let me go to the next slide. Istituto Italiano di Tecnologia is the foundation to conduct the scientific research in the public interest for the purpose of technological development. So this is the Institute Center in Genoa in Italy that I'm working on that. So IIT scientific activity is based on the strategic plan and consists of the four main research that you can see on the screen that is working. The main part is the computer division department, life tech, robotic, and nanomaterials that I'm working. So you can see on the right side that a lot of centers in the Italy, also in the world, you can find with the name of the IIT, and this is the building that in Genoa located, and our department centered here. Here there is one video that I cannot play, but maybe later I can separately play from the YouTube. It was just introduction about the IIT. The group of the smart material is based on the Center of the Research Facility in Genoa, and our group is we are around 50 persons. So in total in IIT, more than 2,000 people are working in different departments. In our group, we are around 50. That with I mean, main people are postdoctoral researcher or PhD students, and the team leaders that we are working in these categories that I put it in the screen. So the research of the group deals with the development of the new composite material and combining the various polymers and changing their properties by introducing nanofillers or organic molecules in the matrix. We are focused on these main subjects that you can see, the sustainable biocomposite, food protection, water perfection, green flexible electronic devices, biomedical devices, and industrial smart materials. That mainly I'm working in this part. That we have a collaboration with a lot of the European or out of the Europe companies, and in different category that I introduced to you. So we are working on both the control of the chemistry and the structure of the materials we develop in order to achieve precise properties adjusted to the needs of various applications, the field. Since polymers are the main building block of the materials we fabricate, we have intensified our efforts in using natural polymers, principally of the plant origin of the polymers. So, in order to develop the new advanced composite material at the same time with minimal environmental impact, this is our main goal. Uh, in Today in this presentation, I would like to focus on these three major issues related to thermal interface material. This is one of the projects that we are working here, and now I'm focusing on these part themes: thermal interface materials. It means transfer heat between two or more solid surface to fill gaps between the solid surfaces with the substrate that is got better thermal conductivity than the air in between the surfaces. This is I'm going to explain. First of all, I would like to give you the overview about the sustainable thermal interface material from recycled cotton, textiles, and graphene nanoplates. And next, I will go in situ graphene alignment in self-sealing starchable films for efficient thermal interface material, and then highlight what I'm working at doing on the maximizing the on non-silicon thermal interface materials performance. This is our current project. That is the collaboration with the company. So about the first project, this is the schematic of the protocol, the preparation of the protocol for sustainable cellulose and GMPs non-composite. So effect of the process of the hot pressing on the surface appearance is also you can check, you can see in the script. So fabrication of the thermal interface materials from sustainable resources is very challenging task, but at the same time of the great importance due to the continuously growing problem of the electronic waste management. The variety of the team comprising synthetic polymer loaded with metallic wires or ceramic nanofillers are commercially available. However, they are using frail and difficult to recycle. So in this project, we report the simple fabrication process of the sustainable bio-based teams using regenerated cellulose and graphene nanoplatelets, we are saying GNPs. In the process relies on forming conductive inks by dissolving post-consumer cotton fabric and dispersing GNPs in the common solvent followed by the solution, casting, and drying. So you can see in the screen that the material is the plain woven 100% cotton fabric was used as a model cotton fabric for regenerate cellulose composite. And we are using the TFA as a solvent for dissolving cotton without further purification. So a commercially available thermal pads and clay putty were using as a reference in this paper, and with a thermal conductivity of around 6 watt per Kelvin and 1 uh, for these two. So um, here, just to show you that this is, first of all, we are trying to solve the material in the solvent, in the TFA, and then try to, with the process of the hot pressing, make the samples and going to the around 100 degree and try to make the samples, and then going to analyze all of them with the different the instrument. Here is the SEM image of the sample after the hot pressing. So a scanning electron microscopy can help us to see exactly how it's going on the surface. So as you can see, the cross in the left side, the cross section of the SEM image in different samples, we are starting to load the filler GMPs from the top, uh, 0 percentage, 10%, 15, and 25. And the corresponding surface morphology, the top view also you can see in the bottom and right side. So the pure regenerated cellulose film without any GMPs in the left top, you can see you can see demonstrate the dense structure with no pore or crack formation. The cross-section morphology of the nanocomposite indicate that is relatively the low GNP mass fraction, like 10%, nanopellets are not well intercontact and large graphene-free cellulose on the surface. So here you can see by adding the GMPs, we are changing the morphology of the surface, and also we are by after that, when we load it, we are going to characterize you can see in the image E, we are trying to, with the index, checks exactly our element on the surface, and also with the Raman we are again characterize the surface on the surface on the surface of the sample. So in the EXRD spectra of the raw cotton fabric regenerates cellulose film and regenerate cellulose with the graphene nanocomposite that you can see. And in the E image, you can see the XRD profile of the cotton fabric regenerate cellulose and the samples with 25% graphenes. So it shows two characteristics: the peaks at 22 and 14.8, with the shoulder at 16 and 34, associated with the cellulose structure. Um, Here, for the image F, again we are showing, we are working with the Raman, with the laser 514 that we have in our laboratory, and also the range that the spectral range scanned is in the range of the 400 to 300, 3500. And in the right side is about the mechanical properties. We try to check the stress strain curves of different GMPs mass concentration. So you can see with different loading the graphene 0%, 5%, 15%, and 25%. And the commercial sample also have been included for comparison purpose. So we checked and showing the young modulus from all corresponding samples, that's mainly with the 0 and 30%. So mechanical characterization of the cellulose or with the graphene nanocomposite were analyzed with the instrument, dual column, the table top, in the system that we can measure and characterize exactly the tensile measurement, and we try to collect in 5 different specimens for each sample. And the young modulus, the slope of the curve uh, before the yield point that you can see extracted from the engineering stress strain curves and reported with the standard deviation. Here is the schematic diagram of the thermal conductivity system, similar to the chip stack configuration in the electronic devices. Um, we are trying to make the real model in real applications similar how if we are using our sample what happened in the real applications. So thermal performance of the prepared samples were measured using the experimental method resembling a chip stack electronic configuration. So you can see here we are using two 1 centimeter thick steel block were stacked on the top of each other. In the next slide also I will show you the real image on the top of each other with the size of around 4 to 4 centimeter square, and the non-composite were sandwiched between the blocks under the ambient conditions. So continuous heat is supplied throughout the duration of the measurement, but the hot plate from the bottom metal block. Uh, Thermal properties of the prepared cellulose, the graphene nanocomposite, and two reference material that I told you is the commercial around 6 and 1 watt per meter Kelvin were characterized by placing them between two steel blocks, and the bottom steel block was directly in contact with the hot press at temperature around 90 degrees. So whereas the top steel block was at the room temperature, replacing an electronic procedure and heat sink configuration. So here then you can see in the image, heat was supplied throughout all the duration of the measurement by the hot plate to the bottom metal block. And another metallic plate of the 300.5 kilogram corresponding to 2.15 pressure was used as a pressing force during all the measurement from the top. Uh, and an insulating Teflon sheet we are using with the 2 millimeter thickness was also used between the top steel block and the pressing weight to avoid any thermal dissipation. In order to ensure tight the inter in the let's say the for using this the weight on the top, we want to be sure that we have enough pressure to shows the heat transfer between the two blocks. And also we are in the right side, we are here the surface heat transfer or temperature distribution was also estimated by theoretical model. We trying to shows also improve that our real experimental is similar to theoretical model. Um, Let me go to that next slide. So the here is the we try to measure this heat transfer with infrared camera that so you can see in the left side we are putting our teams in between, same like the sandwich in between the two block, and then we are comparing also with the commercial. Again, my video is not playing, so maybe separately later I will share. And so this is the representative sample of the data collecting of the average temperature T1 and T2 from experimental setup and infrared thermography. So how we are collecting the data, I will explain that after placing the prepared team in between the two blocks, we are showing the above decrease in average temperature of the bottom still block and increase in average temperature of the top still block were recorded using an infrared camera. For this, a certain rectangular area near the mating interface in both steel blocks were selecting using the FLIR Research IR software that we are trying to analyze the data. And then we are recording the temperature profile, and in the right side you can see we are comparing one by one that how the temperature goes down between the two blocks. So here in the plot D, temperature of the bottom block T1 cooling down, we are calling, and the top block T2 absorbing heat for different sample we are measuring. And in the plot E, temperature gradient profile for corresponding samples as a function of the contact time. So the temperature differences or the temperature gradient we're calculating and using them in the T1 minus T2, and then we are the measuring one by one data collecting in different area of the surface. We are collecting the data, making the average, and then comparing all these profile, and then using to estimate the thermal conductivity of the prepared nanocomposite, and we are reported in comparison with two reference material, the commercial that we used. And here is the SEM image of the cellulose graphene with 25% coated surface that is clearly you can see on the surface. And also about the right image is the temperature distribution at 2D in different time. So we are showing aligned the X direction of the coated surface, um, how the heat transfer on the surface. So here shows after 100 seconds, approximately one third of the surface area change its color due to the conductive heat projection access to the surface under the surface convection and radiation losses. So uh, in conclusion about this project, we have fabricated highly efficient thermal interface nanocomposite based on regenerated cellulose from the textile waste. Uh, let's say note that other sources of the cellulose or pure cellulose can be utilized as a natural matrix if desired. So um, um, moreover, in the developed nanocomposite display good electrical conductivity, and also the solution casting method allow potential recycling of the themes after the using this. We estimate that the bulk thermal conductivity of the cellulose nanocomposite is around the 5.5, and so future work will involve softening these nanocomposite to putty like soft rubber. So this is also another project that we are working about that. Uh, in situ graphene alignment in self-sealing stretchable films for efficient thermal interface material. This is another project that we are trying to use the parafilm in the process in combined uh, with the GNPs, and we try to characterize these samples. And especially is important for us to about the thermal interface for the material, but we have new process for making alignment the sample to improve the thermal conductivity. uh, Although graphene nanoplatted GNPs and the carbon nanotubes CNTs are known as they demonstrate significant potential as a functional fillers to improve the electrical and thermal properties of the polymer. Uh, so aside from the state of the dispersion, the level of improvement has been found in strongly correlated with the in situ orientation. So, however, achieving the orientation within the polymer present a significant technological challenge. In this paper and project, we show a simple and repeatable thermoforming process to fabricate high thermal conductivity GMPs nanocomposite pads, and using the self sealing searchable film that we are using the parafilm. The pad that you can see in the screen that can the sliced and turned in the vertical the stack and fused into the new pad due to the self-sealing nature of the paraffin. Hybrid pads were also constructed with MVCNTs, multi-walls. So the process that you can see is we combine GMPs with the perfume, and then making the ball formation, and we try to press on the screen. uh, I cannot. So the pressing with the hot press in the temperature around 60, and try to make the film. And then after the hot pressing, we try to there is one horizontally oriented about the GMPs. Also, we try to cut and make it vertically oriented. So uh, here is the samples that we worked, and we try to compare only um, uh, GMPs, and also we call hybrid, that mix of the GMPs with multi-wall MV. Um, so the formulation of the fabricating carbon-based paraffin nanocomposite samples and different ratio is in the table. We show so uh, from here on, the paraffin will be designed as the PF that we call PF here, or we fabricate various the GMPs with PF and nanocomposite having the GNP concentration ratio from the 30 to 60, and the hybrid that is the combine of these two filler with the PF, and the ratio from 10% with respect to the GMPs, namely 3 to 6%. Um, so here in the SEM image, we are exactly showing or improving how we can change the orientation of the fillers. Sorry. So in the left side, about only the image with the GMPs, we are showing the how vertically alignment the samples with G30 and G60 we call. So in the top is after hot pressing, and in the right one, when we change the alignment of the filler, vertical alignment. So also in order to access the morphology of the nanocomposite material, we try to check all the surface with the SEM, scanning electron microscopy, and with different magnification. That is, for example, for this one is 2000 magnification that we are zooming in the surface. So also in the right side, you can see the cross section of the PF with 33 percentage. We called H33 in the table. And after the hot pressing in the left one, in the right one also, after vertically aligned, that is clearly you can see in the surface of the samples. And for the bottom, C is the cross section SEM image of vertically aligned PF with 66 percentage. Uh, and similarly, for the hybrid system with the MWCNTs, open the process with hot compressing molding, the GMPs were also aligned with the multi-wall carbon nanotubes network that is clear in the bottom image right side. So the horizontal and vertical MCNTs appears, and we always aligning with the base plate of the GMPs in our samples. Uh, Here is this figure shows the schematic of the thermal conductivity measurement system for the non-composite pad that contained horizontally and vertically aligned GMPs. In the case of the non-composite, with horizontally oriented GMPs, the applied heat flow direction is orthogonal to the orientation direction. And for vertical alignment, the heat flow is along with the GMP's basal plane in plane. So in figure in the plot in middle of the screen shows the true plane thermal conductivity measurement of all non-composite samples. And so in the sensor, we try to put our sample and measure the thermal conductivity with our system TCI. And you can see that we are trying to compare the differences between the aligned sample that we oriented the feelers of the each sample with the bulk one. So uh, you can see is the big differences when we wanted to compare the with the aligned sample. And so paraffin alone is has the very low thermal conductivity, is around zero point 0.2, and which independent of the hot press condition. uh, Thermal conductivity of the horizontally aligned GMP's pad is higher than the pure paraffin for sure, but even at the high GMP's loading, 60%, the thermal conductivity increased by 5 times to around 1. But here we are showing the hybrid sample, that is the combined with the MWCNTs in this nanocomposite. For example, compare the sample G60 with the hybrid 6366, does not enhance the thermal conductivity further. Non-composites such as these two samples, same like the 50 or the 60, G50 and G60, uh, showing that we have the big difference in according to the thermal conductivity. So here in the right side, the table shows the summary of the published work on the thermal conductivity of nanocarbon thermoplastic polymer-based composite produced by various processes. So here it shows the list of the numbers with different thermal conductivity values, and various fabrication processes have been implemented to manufacture thermally conduction nanocomposites, such as injection molding, extrusion, melting, solution mixing, and vacuum drying. Sorry. So here, mechanical properties, we are trying to check the mechanical properties of the sample. And the here is the stress strain curves of different non-composite samples containing only GMPs in the number A, and with hybrid content of the GMPs and the MWCNTs, as well, including with the on-film PF, the matrix. So it's clear in the left side of the plots. Uh, and Plot A represents the specimen fabricated for tensile test, Young modulus E, and elongation at the break percentage values obtained from the non-composite samples set GMPs in the plot C. So we are trying to compare all these two category of the samples and check the elongation and the break percentage value of each that shows clearly big difference between these samples. And the mechanical properties of the non-composite pads after hot pressing were measured to obtain elastic modulus and elongation at break values. Uh, so the unfilled the PF sample is a highly elastometric soft polymer with the elongation at break value of the 260 percentage and elastic modulus of about 23 megapascal. Adding 30% of the GMPs reduced the elongation at the break values of the 60% with a slight increase in elastic and or Young modulus. However, adding the MWCNTs in these nanocomposites resulted in a significant recovery in the hybrid elongation at break value that was measured to be 200 percentage. In fact, adding the MWCNTs improve mechanical properties of the GMP's field PF nanocomposite by improving elongation at break values and ductility. So, in summary, it may be stated that all the hybrids are highly suitable for compressing molding, such as the cutting, performing into vertical alignment. They can also be recycled and reformed into the desired format, depending on the application. So by using the compression molding hydraulic hot press that we use, we fabricate graphene-based thermal nanocomposite pad with high thermal conductivity using a self-sealing stretchable film known as perfume. And the hybrid pads were also fabricated with multi-wall the carbon nanotubes, MWCNTs, uh, that shows and the with different concentration, the corresponding to 10%, and to 60%, 63%, significant. We showed that the significant enhancement in thermally conductivities we measure. So the another project that is our current project we are working, and this is in the collaboration with the Thermexic Nanoramic, the company in the USA, is focusing on the maximizing non-silicon thermal interface material performance. So we are trying to we have some goal to explain about the to make about our current pad. So generally we are focusing on the pad, not paste or putty or liquid thermal interface material. We are focusing on the pad, and the the factors we should consider is the form factor that is important for us, not grace, not paste, and or gels, and thermal conductivity. High performance thermal conductivity is very important in this in compared to the commercials, and also about the compression data, the hardness, deflection, and compression set, and design and the application factors that we are trying to find the perfect application for our paths or samples. And also we are focusing on the electrical insulative, so uh, non-silicon samples, try to ignore using the silicon in our path. So just to briefly explain that in the non-silicon thermal pads, in the commercial we have a lot of the pads with the silicon chemistry, so we are trying to provide the thermal stability, high thermal stability, and conformability, and also about the reason that some reason that why we are not using the silicone. The main part is the about the oils that is the leaching from the pads. So we are trying to ignore using these materials, and adhesion failure, electric shorts. Also, uh, we are mentioning that the performance or the thermal conductivity is not high such as we want for the industry application. And so definitely break down the pad during the high pressure, and also outgassing is the big issue for us. And so we believe that we have to avoid using the silicone. uh, the advantage of the pad, that the film, the pads that we are working on, that we are, the reason is that no mess, there is no mess. So simple pick and place and fills the bigger gap. So typical pad are available for half millimeter. So we are working on the thick samples to fill the gap between the two solid surface, easier in installation, so can be uh, exactly make the size or the form, or 2D or also 3D area we can cover completely. Also another process that we are preparing is the coating, so we are trying to cover completely all the complex surfaces. So one kind of the product will be the electrical insulation, so safe for electric transfer pass, and also material compatibility. Some paste compound can be um, completely covered on the substrate. So uh, we are trying to also cover this part, and reliability, better long-term performance, open power cycle, and mechanical vibration. Uh, Here, the just to shows that the how much is the our sample is stable. So we are trying to analyze with the thermogravimetric analyze TGA, and showing that our sample or our material film is stable in high temperature. As you can see, is going to up to 200. And also here we are showing that the stability for the sample, you can see without any resin and oil separation, our pad, thin pad, after the long time hours in the temperature over the 100, still is uniform, and without any damage on the surface. That we can see is clear in the real application, is the damage the our systems. And so about the different qualification overview about the different application that we can use it. So we mentioned here that the different automotive power suppliers and also the high power LED applications, so semiconductor assembly, so and 5G telecom, and also within the aerospace and defense, we can use huge application according to the transferring the heat from the heat source to heat sink. In conclusion, uh, the key consideration when selecting teams, and we it's important for us to have the good gap filler and performing better than other commercial teams and easy installed and n- there's no residual on the system on the remain carbon based filler is very we are focusing on that non-silicon and also the low thermal impedance. So in different we have two different kind of the samples, that one of them is the high thermal conductive, 2-3 times higher than the commercials, and also another one that is the white one is the electrical insulative. And so yeah, this is also we are mentioning that what's our solution about the non-silicon high temperature resin system and ultra high thermal conductivity without escape facing. So thank you so much, and for let me uh, again thank you all for joining here today. And also I want to a special thanks to Dr. Iman also for organizing this interesting and useful conference. If you have any questions, I'm happy to answer them. Thank you.
Reza. Thank you, Dr. Amir Reza, for technical seminar speech and for the very interesting session. We are very much honored to have you with us today. Now we take this opportunity to open for the question and answer session to our seminar speaker. Uh, if there is any question from the comment bar, so I can read the questions on behalf. If there's not any question, maybe I can ask one or two questions. All right. Doctor, how is the process of fabrication of a hybrid pad by compression molding?
Yeah. Yeah, so I try to a little bit briefly explain, but I mean has a lot of details about these following steps. But about the fabrication of the GMPs with the parafilm nanocomposite, so we are trying to cut into the desired square shaped films, and try to manage it and calculating exactly how much GMPs with multi-wall powder we gently place over the film. So the films were closed like the envelope in the punch of form, self-sealing for the nanocarbon powder inside. So we try to, after mixing or combining with the hot press the machine, the hot press the instrument that we have, it higher, I mean higher than 2 tones or something. We try to press these samples to combine very well the all the materials. So we try to increase from the half tones to 3 metric tons, and we repeat 5 or 6 times by the folding the hot pressing film into the punch, one more or so, that we are sure that the GMPs can be dispersed in the polymetric matrix. Yeah, so
Okay,
then we are
sure.
trying
Thank
to
you.
confirm with the SCM exactly how it's going on, how disperse very well the material. Yeah.
Thank you for the complete response. And one more question. How to collect the data onto samples with IR camera?
I don't know. It's possible for me to share one video. Maybe this is good to show because I added in the slide,
I
but
think I think it would be possible.
I add in the slide, but uh, maybe it's more clear if I can share share screen and then yes. So can you see this? Can you see the video?
Yes, we can see.
Yeah. So here is the our let's say the process of the measuring our samples or pad between the two blocks. I mentioned that thermal performance of the prepared samples measure using the experimental method resemble the chip stack electronic configuration. So here we are putting two 1 centimeter thick steel block and on the top of each other, and then the same like the sandwich process, we are trying to measure the collecting the data. So you can see after placing then the team in between these two in the as shown above, decreasing average temperature of the bottom steel block and increasing average temperature of the top steel block uh, can record it. So you can see by changing the color in the top, we are showing that how much fast the heat transfer from the bottom to the top. And then we are
Right.
trying to compare all the samples and with the commercials to calculate exactly how is the thermal conductivity.
Thank you so much. Thank you for your answer. Okay, ladies and gentlemen, we will proceed for our second round of parallel session, starting from 5:30 p.m. until 6:30 p.m. Malaysian time. Kindly proceed to their respective session A, B, and C. Please be informed, everyone, the closing ceremony will be started from 6:30 p.m. Malaysian time. Kindly join us for the best presentation award winner announcement and short talk on publication by the organizer. Happy conferencing to all of you, and thanks for supporting us. Thank you.